So, welcome everyone. Thank you for the opportunity again. I would like to present our joint work with Gábor Sági, to whom I will refer to as Gábor rather than Sági, if that's okay for everyone. And I would like to talk about automorphism invariant measures on homogeneous structures. Okay, so first a small introduction, then I would show some previous results, so to say, which are also recent, but not the most recent, which will come after that. Those will be our results mainly. So our our setup is the following. We have a set, let's call it A, on which a group, a topological group G acts, and we want to characterize the G invariant measures on A. That's our goal. That's the purpose of the current presentation. And for a quick refreshment, the term amenable originates from Neumann, and he said that the group G is amenable if there is a G invariant finitely additive probability measure on G. This notion can be extended to both a structure and a theory too, by defining a proper measure on the proper subsets on the structure or on the stone spaces. So now we have this triangle with a structure, the theory of a structure, and the automorphism group of a structure. And while the current presentation is not mainly about this triangle, but in the back of our minds, it could be interesting to note which sort of directed edges or implications can we draw into this triangle. Before we continue, I would like to introduce a new notion, which is the set of automorphisms of A with finite orbits. This set will be called this out fin A. And regarding this set, Gábor showed in 2021 that if a structure is both countable and strongly Alav-zero homogeneous, and this set is dense in the automorphism group for all and all of its products, then a finitely additive automorphism invariant probability measure, or so to say, automorphism invariant probability measure exists on the Boolean algebra generated by the elementary open subsets of the automorphism group. Also, Hrušovský, Krupinski, and Pillai showed in 2020 that if a structure is both strongly Alav-zero homogeneous and Alav-zero saturated, then the following two statements are equivalent. That is, the automorphism group of A is relatively amenable, which is not exactly amenable, but is similar to it. And the theory of A is amenable. So now in that triangle that we have in our mind, we have a sort of back and forth implication between the automorphism group and the theory. Not exactly, because it says only relatively amenable. And based on this, Gábor showed it in 2021 that if our structure is countable and saturated, and this set is dense in every product of the automorphism group, then the previous two properties hold actually. So the automorphism group is in fact relatively amenable, and the theory is also amenable. The theory of the structure, of course. while the current presentation contains both theorems about both the existence and unicity, I would like to emphasize that the main point of this presentation is about unicity. So many of these existence results are or were already known, and our current addition to it is about unicity. But for completeness and consistency, I didn't want to leave existence out. So first we start with a set and the subgroup of its symmetry group, which is compact. So the subgroup is compact. And we are curious, what can we say about compact subgroups? Then later we would like to ease the requirements a bit. That is, maybe if our group is not compact, then some weaker notion might be enough for what we want. Okay, so first we have a set, a subgroup of its symmetric group, which subgroup is compact. And then we can say that that a G-invariant finitely additive probability measure actually exists, but only on the Boolean algebra of the clopens subsets of G, so not on every subset, unfortunately. And also, if we extend this measure to the sigma algebra generated by these clopen sets, then it will be sigma additive. And also an extension of this measure onto the sigma algebra. So now the domain of this measure is much better. Also, if this extension is G invariant, and if the original set A is countable, then this extended measure on the sigma algebra generated by the clopen subsets is a probability measure also. Now, what can we say about unicity? We can say that this measure on only the Boolean algebra is the unique G-invariant finitely additive probability measure. And also the extension of this measure onto the sigma algebra generated by these clopen subsets is the unique sigma additive extension onto this sigma algebra. Now, we have this for sigma additive property, but how about an extension onto the sigma algebra generated by these clopen subsets, which is finitely additive, so not sigma additive? We don't know yet, but it would be interesting to see. Okay, so we know what we know about compact groups. Now let's try to as I said, ease on the requirements a bit. Let's try to define a group which is not exactly compact, but is close to it. And for that came sigma star compactness, which we define by saying that a group is sigma star compact if it is an increasing union of groups where each group is a subgroup of its of the one following it. So as you can see by property 1, for each n, Gn is a subgroup of Gn plus 1, and also they are compact. So for each n, Gn is compact. This says that G is not in fact compact, but is very close to compactness. And Gabor also showed that this property is equivalent to the previously mentioned set having a dense property in the automorphism group. Using this new notion, we try to say something about if we had a set A and a subgroup of its symmetric group, which is not compact, but sigma star compact. Then if we suppose that such a G invariant and sigma additive probability measure exists, which is also defined on the compact subsets of G, then very interestingly, we get that G has to be compact. So that means that if we are looking for a sigma additive probability measure, then sigma star compactness is of no good use to us. It is a dead end. We have two possibilities left. We can, so we have the possibility left to change our requirements. That is, we can consider finitely additive or sigma finite measures. But if it's strictly sigma additive, then we can go no further. Okay, so let's try to change the requirements a bit. If we have a set which is countable and we have an increasing sequence of compact subgroup of its symmetric group in a way that for any n, we have that the index of Gn in Gn plus 1 is finite. So that is an additional requirement. Let's say that we take the group which equals to the union of these subgroups. So G is sigma star compact. Then we can say that a non-trivial G invariant Borel measure exists on G. It has an additional property, that is, for every compact subset, it has finite measure. And I would like to add in defense of this sigma star compactness property that it is not implied by local compactness. That is, this theorem is not a special case of Haar's theorem, because, for example, the automorphism group of the Rado graph has a locally finite subgroup, which is sigma star compact, but it is not locally compact. Okay, so what can we say about unicity in this case? If we have a countable set, a sigma star compact subgroup of its symmetric group, and we have two non-trivial Borel measures on G, on the group, then we can say, or we know that they are at most a constant factor away. That is, there is a constant for which one of them is the product of the constant and the other measure. Of course, we cannot get any closer, because if we have a Borel measure, then if we multiply it by any constant, then we still get a Borel measure, which is not the same as the one before, so it has different values. And at last, what can we say about, so until this point, we considered compact groups, sigma star compact groups, which was a dead end in one case and led to some results in the other case. And now I would like to show some results in a very general setting. Firstly, I would like to refresh Tarski's result, which says that if we have a finitely additive invariant measure on G on a group, which is the automorphism group of a structure, then we can define the following measure on the structure, which is basically very concentrated on the orbit of. So to define this measure, we have to take an element from A, which we call the origin, and this measure, which we define by this element, is concentrated on the orbit of this element. So when we measure subsets of A, they will have measure non-zero only if they contain elements from the orbit of A. But this measure is finitely additive and G invariant. And also if our original measure on G is sigma additive, then this will be sigma additive too. But as I said, its domain is not the biggest. And also interesting, it's for me it was interesting, I think, or it's pretty fun, so to say, that we can do the same, but in the other direction. That is, if we have a finitely additive G invariant measure on the structure, then we can do pretty much the same for the group. That is, we can define define a measure on the group, which will be finitely additive, G invariant, but unfortunately its domain will be only a Boolean algebra, which is generated by the cosets of the stabilizer of A. of A. But unicity in this setting is also very interesting, I think, because we can say that if we have a measure, a finitely additive automorphism invariant measure, which is defined on all subsets of the structure, then this measure is actually a linear combination, or possibly infinite linear combination, so to say, of measures presented in the previous slide. That is the measures created by Tarski. So every measure on a structure can be made out of these measures taken from the automorphism group. And also, if we want a probability measure, or if we have a probability measure, then it's not just a simple possibly infinite linear combination, but also a convex combination of such measures. So in terms of unicity, in this setting, these measures are, while not as close as previously, as that they are only a constant factor apart or away, they can be constructed in a linear combination of other measures. And as to where to next, or what other interesting questions remain, our goal in general is to understand how specific structures are built up from their finite parts, and for that amenability plays a big role. And and there are many examples of structures which have automorphism groups with dense, locally finite subgroups. For example, the Rado graph, hands-on graphs, and many more Freise limits. And it would be really interesting to see how these are built up based on their finite parts. And that would have been my presentation. Thank you for your attention.